In this video, we are going to be starting chapter 3, which basically will start to look at different new techniques of integration. We saw in chapter 2 that there are many applications of integration, anywhere from finding the volume of something, to finding the area between two curves, to finding the center of mass, to finding the work needed to pump water out of a tank. All those, there's so many applications of integration, and now that we have kind of covered some of those, we're now going to take a look at some more methods for actually finding an integral when it's not as straightforward as what we were used to in Calculus 1. Now in Calculus 1, we did learn how to find an integral using the substitution method, and we reviewed that in this class, but we need to learn some new methods. And so the first method that we're going to learn is section 3.1. It's called integration by parts, and this is essentially a method that undoes the product rule. We saw that integration by substitution method undid the chain rule, but in this case we're going to undo the product rule. And so in this section, the things we're going to learn is we're going to talk about being able to recognize when to use integration by parts. We're going to use the integration by parts method to solve integration problems. So I'm going to show you how to actually do some of those problems. And then we're also going to use the integration by parts method for definite integrals as well. So let's jump into developing this concept of what the integration by parts method is. I already stated that integration by parts is the opposite of the product rule, if you will, the product rule. And so we have here stated the product rule. It may have been a while since you did Calc 1, but the product rule says that when you have the product of two functions, f of x times g of x, the way you find the derivative is taking the first function times the derivative of the second function plus the second function times the derivative of the first function. And so what we're going to do is we are going to integrate both sides of this integration rule, if you will. So we're going to integrate the left side, and we're going to integrate the right side. And when we do that, of course, on the left side, the integral is going to knock out the derivative, so that just leaves f of x times g of x. And then on the right side, let's go ahead and split this integral up. So, because we know that the integral of a sum can be broken up into the sum of two integrals, so we could rewrite this as the integral of f of x times g prime of x dx plus the integral of g of x times f prime of x. Then, of course, we could use some algebra to move things around. And so I could essentially take the integral over on the right. I could take this guy here and I could subtract it over to the left-hand side. And I just noticed that there is a typo here. This should not be a plus. This should be a equal sign. I'll make sure we have that correct. Sorry about that. Okay, so if I move that integral on the right hand over to the left side, we get f of x times g of x minus the integral of g of x times f prime of x dx. And that should be equal to what's left on the right side, which is the integral of f of x times g prime of x dx. And you know, if we were to just kind of flip this around, what we would have would be the integral of f of x g prime of x dx equals f of x times g of x minus the integral of g of x times f prime of x dx. And that right there is essentially our rule for integration by parts. We do make some substitutions to kind of simplify things down. So typically what you'll see happen is you'll see u being replacing f of x, and you'll have v replace g of x. And when you do that, things get much simpler. So you can see here, theorem 3.1, we let u be f of x, we let v equal g of x. Of course, if v is equal to g of x, then we know that dv, we could find the differential, dv would be g prime of x times dx. Hopefully that makes sense. And so then plugging all those things in, so letting u be f of x, v be g of x, and dv being g prime of x dx, and I guess I should say one other one, right? So if u is f of x, then du is equal to f prime of x dx. So making all those substitutions, we get this formula here. We get that the integral of u dv equals uv minus the integral of v du, and you just need to commit this to memory. That is the rule for integration by parts. And the first question we want to ask is, well, when are we going to use this? Well, we saw that with the substitution method, a lot of times the substitution method worked great when we had multiple functions involved, but a lot of times that was when we had a function inside of a function. This is an integration method that works well when we have multiple functions. So when we have maybe two functions, but a lot of times they're functions that are unrelated to each other. In the substitution method, a lot of times our functions were related, and they were related by the chain rule. Let's say this. Let's say we should mostly use the integration by parts method when the integrand, remember that term, the term integrand, that's the part inside the integral that we're actually integrating. So when the integrand consists of two unrelated functions, so that we are unable to use the substitution method. So we have two functions, a lot of times unrelated. In fact, if you look at the examples here below, notice we have two functions. We have x squared sine x. There's no relationship there. Now, if the x squared and the x were reversed, so if it was the integral of x times the sine of x squared, right, then we would use substitution, because if we let u equal x squared, then du is 2x. So that second function x was related to the inside function of our sine function. But in this case, we do not have that. So they're not related. We couldn't use u substitution. Again, in example 2, we have two functions here that are not related. They're unrelated. So we're going to need a different method. And in this case, the method we're going to use is the integration by parts method. Now, the thing that is sometimes the most difficult is if we come back here to our method, there's two parts here. So we notice we have the u part and we have the dv part, and we need to decide which part of our integral we want to let be u and which part we want to let be dv. And there's a nice little memory mnemonic that can help us with that. So how do we know when to choose u and dv for the integral of u dv? Well, I like to use the one on the left, and the one on the left starts with L, which stands for x, and then I, which is going to stand for inverse trig functions, or trigonometric functions. P is going to stand for polynomial. That's when you have like x squared, x cubed, things like that. E, of course, is going to stand for exponential. And then lastly, T is going to stand for trig functions. So how do we use that? Well, Generally speaking, we want our selections for u and dv to give us a simpler integrand to work with than the one we started with. So we're going to, moving down from top to bottom, we're going to let u be the first type of function we see. So for example, in example 1, x squared is a polynomial, and sine x is a trig function. Well, which one comes first on our mnemonic? Well, polynomial comes before trig, so we would let u equal x squared, and we'd let dv equal sine x dx. Okay, so I'm not going to do this example right now, but that's kind of how it works. Now, if you like the other mnemonic better, I can give you that too. The L stands for logs. The I stands for, again, inverse trig. A stands for algebra, which is kind of like the polynomial. T stands for trig, and E stands for exponential. Notice that the order is essentially the same for these two mnemonics, except that the exponential and trig are switched. That's because a lot of times those two don't really matter. But the first three definitely does matter for how you want to pick your u. And that basically does it. So that's the end of this video. We will cover some examples in your next videos. So I will see you in the next video. Thank you.